Okay, negative, we will let it something is wrong. So in the last class we started dielectrics. So let us start from there. So dielectrics is the module number 3. Actually it is dielectric materials. Dielectric materials. Right? So what are the dielectric materials? In the previous class we have already distinguished between insulator and also dielectric. So to recap that one, dielectric materials are a special class of materials in insulators itself. You know there are metals, semiconductors and insulators. So insulators are the ones which do not conduct the electricity, that you know. So but what are the electrics? They belong to the family of insulators. However, the main difference between the insulator and dielectric lies in two ways. One is fundamentally, other one is application point of view. Right? Fundamentally and also functionally. Fundamentally, the difference is when you apply the electric field, what insulators do, they restrict the flow of electricity. Whereas dielectrics, they store the electric energy within themselves, or else they polarize themselves. That is fundamentally. And functionally, the usage of insulators is different to the usage of the dielectrics. Insulators you use at various places where you want to stop the electricity to prevent the current shocks, right? But dielectrics are used in various other applications in the electronics, such as sensors, in the capacitors where you want to increase the charge storage, and various other different applications which we will see at the end of this class, right? So that is the main difference. So by saying that, what I made is all the dielectrics can be insulators, whereas all the insulators cannot be dielectrics. So there is a difference. However, remember that dielectrics is a family of insulating materials, right? So now let us go back and try to understand some of the fundamental definitions. Then we will go back to the derivation. So fundamentally, how do we understand these materials? See, after defining what is dielectric material, what I mean to say is, take a dielectric material like this, any dielectric material. So when you consider a material has atoms, atoms has, what is atom? Nucleus at the center, and electron cloud is revolving around the nucleus, that you know. So let me take you typical atom like this. There are many atoms, but let us focus on one atom. Atom has nucleus and electron cloud is revolving around it, that you know. Right. So when you have such kind of arrangement, the cloud of the negative charges and also the positive charge, they are coincides. Look here, the positive charge is here and the center of gravity of the negative charge is also acts at the same point, exactly at the same point. You see, though all the negative charges are spread around the space, the center of gravity lies exactly at the middle, where your center of gravity of positive charge is there. So equal and opposite charges are there, but they are at the same point. So they cancel each other. Plus Q and minus Q will result into total net charge 0. That's why if you touch any material, you don't feel any kind of charge in you. The simple fact is the center of gravity at positive and negative is at the same point and the total charge becomes 0. That is the scenario when you don't have any electric field. So when you don't apply electric field, or in the absence of the external electric field, your total charge becomes 0. That we know. Everybody knows. Now, the difference comes when you apply the electric field. What happens when you apply the electric field? That is the point you need to focus. So, if you apply external electric field. So, this term called external is important. External, but because you are providing from outside, you connect to a battery or something, provide an electric field. Electric field have the positive charge this side and negative charge that side, that you know. So the direction of electric field from positive to negative. Now the material sees the electric field. What electric field will usually do? Electric field will induce the charges. to certain direction. Electric force is applied when you apply the electric field, right? So what is the electric force acts on a charge Q if the electric field is E? Forget. What is the electric force experienced by a charge Q due to the application of the electric field E? F is equal Q into E, right? So it gives a force to the charges. So now the charges experience a force due to the electric field E, which is equal to F is equal to Q into E. So due to that force, the positive charge gets attracted towards the negative charge, whereas the negative charge cloud will attract towards the positive charge, right? So after the application of the electric field, the positive charge moves slightly this side, the negative charge moves slightly that side. Right? Now there is a separation between the positive and negative charges. So this phenomena happens in all the atoms. This is only one atom I have shown. So effectively what happens is, yet the plates of the material or at the surface of the material, there is development of charges, which should call induced charges. So this charge separation happened inside the material. Now you ask what is when E is not is equal to 0, which means when you apply the external electric field, what is your total charge? Is it 0 now? It is not 0. Now total charge is not equal to 0 because there is a separation between them. They are not cancelling each other. Right? So this phenomenon of producing charges upon the application of the external electric field is called polarization. Okay? Because you are dealing with electric materials, this is called electric polarization. Simple thing, you need to understand what is the polarization phenomena. Polarization phenomena is nothing but the, whatever I explained. Now let me define. In the previous class I defined something called electric dipole. Right? So what is electric dipole? Dipole. Two poles are there. Remember, if you absent electric dipole, two poles, two polarities should be there. What are the two? You have one positive, you have one negative. So when the positive and negative charges, they are separated with some distance, you are calling it is electric dipole. Or else equal and opposite charges separated with some distance is called electric dipole. Simple phenomena. So because it has polarity, it will not stay simply like that. It will also have some kind of movement with this. So each electric dipole has something called electric dipole moment, which we usually denote with small p, which is equal to your charge and distance between the charges. These are some other simple definitions. So small p can be written as, if my charge is capital Q and the distance between them is d, or 2L in some textbooks, it is Q into d or else Q into 2L, anything is fine. Okay. So d is the separation between these two charges, and it is minus Q and this is plus Q. So two equal and opposite charges separated by a distance is called electric dipole. Such electric dipole has something called electric dipole moment, which is defined as the charge into distance between them. Now what polarization, electric polarization phenomena is nothing but you are simply creating dipoles. See here, right? Previously without when you don't apply the electric field, in the absence of the electric field, the positive and negative charges are at the same point. That's what I said. The center of gravity of all the negative charge at this point. Similarly, the center of gravity of the positive charges also at the same point. So 2 equal minus Ze plus Ze. Z is the atomic number. E is the charge of either proton or the electron. Okay. So if it is an electron cloud, total charge you will call it as minus Zt. If it is positive charge is plus Zt. So when minus Zt and plus Zt are at the same point, two equal and opposite charges but at the same point. So your D becomes 0 though you have some charge. So your dipole moment also becomes 0 in the absence of the electric field. Are you getting? Okay. So but when you apply the electric field, now there is a separation between them. So charges are there and also distance is also there. So dipole moment is no longer 0. Right? So that is the beauty of application of the electric field. So upon the application of the electric field, actually you are creating dipoles inside your material, thereby you are getting a net polarization or its net dipole moment. You are inducing the dipoles and dipole moments. The process of inducing the dipoles is called polarization. Okay. So that is the electric polarization phenomenon. And you observe here, okay, after you writing, you observe the diagram. There is another observation we need to make. If you have any doubts now at any point, please ask me. However silly it looks. No, don't be silent. You should ask the question. Is it clear up to now? No doubt now. Observe the diagram now. You applied electric field externally, that is E. Okay. Inside also electric field is there. Yes, now look at it. So inside what is the direction of electric field? Direction of electric field is actually positive to negative. If you see inside your dielectric material has the electric field in the opposite direction. So let us call it as whatever it is, E1, fine. E1 is opposing the direction of your electric field, applied electric field. So if I want to know the net electric field or resultant electric field, what would be? We call resultant as ER or E0, whatever. No, different textbooks have different notation. Okay. So what it will be? You are applied E minus inside electric field E1. Or in the textbooks, how they call is many textbooks applied is E0 and this is E1. Then your resultant is E0 minus E1. That is the usual notation many textbooks follow. So let us stick to that. E is nothing but E0 minus E1. Right? So at the moment, let me stop here. Maybe in the next discussion we will take it forward more from here. We will get a relation between three terminologies that I will tell in the next class using the same relation. Right? So this is the resultant electric field. Now you created dipoles and each dipole has its own dipole moment and like that so many dipoles are there in a given material. Now you need to look at overall what is happening overall. So suppose there are n dipoles inside. You created n dipoles. How did you create n dipoles in the material, electric material? How you could achieve that? By applying the external electric field. Don't forget that. So you created n dipoles by applying external electric field E, and each dipole has dipole moment. What is the dipole moment we call? P, small p, small p. Then I asked, what is your total dipole moment? What is the total dipole moment?
Summation of all the dimensions.
I gave you two parameters, from that you get
N into P.
n plus p or n into p, right? So the total dipole moment is called n into small. This is called as electric polarization. Electric polarization. So this is another definition, and this is denoted with capital P. Electric polarization. Electric polarization is actually it talks about net phenomena, overall phenomena in the material. It's not focused on single dipole. Polarization means it is actually looking at entire body. So if there are n dipoles you created by simply applying the electric field, then each dipole has dipole moment P. Then overall, if you are talking what is the polarization, it is nothing but capital N into P. Right? It also has another definition, or else another definition is my polarization, electric polarization. Whenever I talk electric, I have to use, because polarization also happens in magnetic materials. That is our next module. We'll discuss. So the electric polarization can also be defined as dipole moment per unit volume. This is another way to define. Again here you are looking at entire volume of your material, not restricted to a single dipole. Okay, whenever you use the term polarization, which means you are considering complete body. Okay, remember, here or here you are looking at complete body. So follow dipole moment by unit volume. Dipole moment is small p by unit volume is. Let us simplify. What is the dipole moment? Q into D. Volume of simple cube for us. Take a cubic material. So what would be the volume?
Area into length.
A is not there now. A means the side. D is the side. D cube. Or else it is rectangular. D into A. Something like that. So for simplicity, you take a cubic material. It's D. So it becomes as Q by
D square.
D square. What is D square? Area. So Q by A. So polarization is also your charge by area. Charge by area is called polarization. But it also has some type. Surface charge. Surface. Volume, if it covers volume charge density. So surface charge density is denoted with what symbol? Rho. Sigma. Yeah, because it is surface charge density. Or simple sigma is also there. See how many relations came up. You have to know. The following are simply looking like geometry. So your P is Q by A. We'll use these relations sometime when we are deriving.
Call. Sir.
Call.
Call.
But reject the problem. Rejected?
Yes, sir.
Good. You have to learn to reject certain things in life.
Oh.
Don't accept. Especially girls.
Yes, sir.
Because you guys will force like no mad.
Sir, can I reject again, sir?
Reject again. That's what happens in life. Girls, you see, you will be approaching again and again and again. But you have to reject it. Or else block it. Put it in the flight mode. One principle we have to learn. Rejected anybody?
Yes, sir.
He looks so sad, sir. You rejected? Somebody, no? You accepted?
Sir, that time rejection. I guess something important, sir.
How much time we have still? Okay, no problem. Five more minutes I can spend on basics, then we'll go back to actual derivation. Then let me also define some other terminologies called dielectric moment is over now. Dipole moment is over. Dielectric constant I will All of you perform no dielectric constant experiment. So no need to define, you will only define. After the experiment, dielectric constant. Usually it will be denoted either with K or else epsilon r. 2 will use K or epsilon. So who will tell what is dielectric constant? Each dielectric material has a value called dielectric constant. So what it is actually? Who will tell? Because you all performed the experiment, you should be knowing. Who is saying that? Define, somebody define what you understood when you measured dielectric constant through the experiment. What is it? Speak up. I should take Viva from all of you. Nobody is simply going. No? Connections is. Yeah, please stand up and tell now. Very good. Yeah. That's all. Stand up, dear.
Ratio between the property of permittivity is equals to the LED.
Any more tries?
Epsilon by epsilon naught.
What Ullas, you were saying something?
Permeability.
Permeability, magnetic field.
Define now. If you go back to the Viva questions after your experiment, all these questions are there, question answer. But you are not bothered to study, right? Okay. So dielectric constant is a number actually. When you know that number, you will know about the property of that material. Remember what I said is, if I know your bank, not number, account balance. Balance is also a number, not the bank number. Account number has nothing. If you have amount inside, the balance if I know, that number actually gives us an idea. If your bank balance is some like 1 crore, most of you are no rich people I know. Then immediately, see, the moment I say it is 1 crore, you will know, okay, this guy is rich, right? If it is some 10 rupees like my balance, you know that, okay, he is a poor, right? So the number signifies something. Yes? So the dielectric constant is also a number. It gives an idea about its property. What is that property? The property is nothing but, see, what is dielectric material itself? What is it?
It's a kind of insulator.
No, what is dielectric? What you understood so far, what is the dielectric material?
It's a
Polarization. Or else it has the ability to store the charges, right? So same thing, this constant also gives how much you can actually store the electric energy inside you. Simple. Okay. So it is defined as dielectric constant. It is a constant which actually gives an idea about how much electric energy can be stored or how easy you can polarize, in other words. Right? In terms of electric field, if you want to define, it is E0 by E. Okay. In terms of capacitance, we defined in our experiments, because we already spent a lot of time in the experiments, I am not discussing in detail. What you did? You kept a dielectric material inside plates of the capacitors. Then you observed that the capacitance increased when you placed the dielectric material. Okay. So, if you change your dielectric material, the capacitance value also changes. So, by simply keeping dielectric material inside the plates of capacitor, capacitor has two simple metal plates, inside nothing is there, but when you keep the dielectric material, the storage amount of the charges shoots up by the amount of that material's property called K. Okay, how much capacitance it changes? Previously it was some G is C0, then when you keep the dielectric material, K into C times, the capacitance increases. So another way to define is C by C0. Epsilon by epsilon naught or epsilon naught by epsilon? This is correct. What is epsilon? Permittivity of the free space is denoted by epsilon 0, which means it decides how much electrical lines of force should pass through certain material. So if there is a medium, it also has certain permittivity, which means it will decide how much you are applying the electric field, but those electric lines of force should pass through you. Which is, if you smile one more time, you come here. This I am calling you, come here first and stand up. Don't be notorious, man. And stand till the class. So permittivity of the free space is denoted with epsilon 0, not visible to the guys at the back. Yeah, it is blocking your path, no, let me. Whereas epsilon is the permittivity of the medium. If you take the ratio, again it is dielectric constant. This is no simple definition. So it gives an idea about how much electrical energy can be stored in the medium, or how much capacitance you are increasing by keeping the material inside it. Right, that is the dielectric constant definition. Then let me also define quickly electric susceptibility. Susceptibility. Susceptible. What is the dictionary meaning? Susceptible. How much susceptible you are?
Capable. Capable.
Capable. Susceptibility is your ability to handle, in other words. Okay. So I keep on teaching a lesson, you can't susceptible to that. No, after a certain point of time, you will lose your. So when you are applying electric field, what are you doing by applying the electric field in a dielectric material? Why are you applying electric field?
Make it more susceptible.
You are creating dipole moments and finally polarization you are creating. Okay. By electric field, you are creating polarization. If I increase the electric field, what happens?
Polarization.
The charges still move further, which means dipole moment increases. When the dipole moment increases, polarization also increases. Okay. So when you increase E, your P also increases. Therefore, what I say is, actually the polarization is proportional to electric. Polarization is vector and also electric field is, because they have magnitude and as well as in a material which direction you are applying electric field. This, so many ways you can apply. Similarly, charges when they are displacing, which way? this way polarization or this way, depending on the direction of the electric field, right? So how long you can? You are keep on increasing the electric field. Can you keep on generate the polarization in the material? That's the idea. How much polarization you can create? Is it infinite process? Not right. Yeah. There is a limit where you actually have to stop. So the proportionality constant gives that limit. If I take out the proportionality constant, I will call it as phi, and it is related to the electric field. So let me call phi A and E. So this chi is called susceptibility. Susceptibility is a one parameter which actually gives you an idea how much electric field should I apply. You know, for person to person, as our ability changes, material also has. You know, they cannot take more electric field. If you give more electric field, basically you are destroying it. Okay? So while you apply the electric fields, you have to be careful. That's why while you perform the experiment also, we say that you don't go beyond certain limit of current. Why do we say that? They cannot take it, will destroy it. So simply, by knowing the parameter chi is nothing but P by E, chi is equal to capital P by E. What you know is, what is the limit of susceptibility, or else how much maximum electric field you can apply in order to generate the polarization. That is the idea of it. Okay? So answer this simple question, then you can say, what is chi? Is it a vector or a scalar? Answer that and you can.
Scalar.
Scalar? Why do you say that?
Because only magnitude is important. It has no direction.
There is no direction. What is it? Swati, what is it? Chi is. Don't copy now. Vector. Why scalar?
It's a ratio.
Because it's a ratio of 2. Yeah. Your answer is correct. You can say. And your answer is. Chi is actually tensor. You know, in textbooks you read it is a scalar. Of course it is true. But let me say chi is actually a tensor. What is tensor means? Tensor. Have you heard of this? Tensor of rank 2, tensor of rank 3 in the mathematics you might have heard of it. Hey, forgot it. Matrices. Matrices has tensors. So what is tensor mean? See, what we are doing here, you are applying electric field, creating polarization, right? That's what. Electric field has a direction, you are applying electric field in certain direction, creating polarization in also in certain direction. Now this chi should give the information about the directions as well, though it is a scalar. It's not just a number. When you got this number, okay, where I got it, which direction I got. You applied the electric field. Suppose this is our dielectric material. Take. I applied the electric field in this direction. Charges has all sort of freedom to move the way they want depending on the structure. We'll discuss about the structure in our module number 4, but depending on the structure, the charges move inside the body. So if I apply electric field in this direction, so the polarization, which direction it is happening? All possible sort of directions it can happen, but predominantly what direction you want to know. It can be this direction or this in between, certain direction. Polarization, the measure of polarization. If I am applying my electric field in x direction, xx. So if I am also measuring my polarization in same direction, then I call P xx. You apply electric field, first term always denotes application. Second term, in what direction you are measuring. When I say it is chi xy, let us say my phi is xy. What I am saying is, okay, you applied electric field in x direction and polarization is in y direction. So measuring polarization in y direction. Okay. So like that, if I write phi, the phi matrix is having all sort of direction. I can apply electric field in x direction, y. I can measure polarization in y direction. Xy, phi z, like that. Three-dimensionally you can apply and also you can measure. Okay, it is 3 by 3 matrices. So when you have certain kind of arrangement, you say phi is actually a tensor of matrix of rank. What is the rank? 3.
3 to 3.
So that is the meaning of susceptibility kind. So how much time we have? I think we can't do any derivation. Okay, one more. Is it understood? Electrical susceptibility. Okay. So in the textbooks you will not have this much explanation. Simply they will give the definition and they say chi is a scalar. But don't stop there itself. Swati, where are you standing? Yeah. You are a good girl. Yeah, chi is a tensor. Remember. Now, after the electrical susceptibility, let me also define electrical. What is it? Permittivity is over. Polarizability. Electric polarizability. This name itself says what it is. Polarizability. It is defined with alpha. Polarizability. Name itself is giving, what is it? Ability to polarize. So you are taking a material. Now you are looking how easy I can create polarization, or what is the ability with which we can generate polarization. Ability to polarization. How do I define it? We have to go back to the dipole, which means by applying the electric field, you are polarizing the material means you are creating the dipoles, right? So each dipole has dipole moment. So the dipole moment is small p. The generated dipole moment is proportional to again your electric field. Right? If you apply the more electric field, you will get more dipole moment. So if I replace my proportionality constant, I can call it is alpha. This is alpha. This is proportionality constant. Alpha into. Again, these two are opposite vectors. Then the dipole moment polarizability alpha is nothing but small p by capital P.
What's the difference between susceptibility and polarizability? What's the difference between those both?
What this parameter gives?
Polarizability.
No. Alpha gives how much dipole moment you are generating by applying the electric field. Whereas chi gives polarization, capital P. Overall you are looking at. And also it gives the sort of cutoff for the electric field also, how much I need to. So this defines dipole moment per applied electric field, whereas chi defines polarization per applied electric field. Capital P and this is small p. There is a difference, don't get. So this is dipole moment per unit electric field is called electric polarizability. If you are creating polarization easily by applying the electric field, your alpha becomes more, which means you say, okay, this material is easily polarizable. You can polarize that material easily. So what you are doing, you are applying electric field you have to create the polarizability. Means what is my ability to teach you? Now, if you are getting good marks after I teach, no, I said no, okay, my ability is good. What is the player's ability? He is hitting centuries. He has good ability. So similarly, any material, by looking at this number alpha, I know, okay, this material is good for me. Why do you say good? Good in terms that I can use this material for specific application by giving little bit of electric field. If you can create, good amount of dipole moment, now it is useful for you to incorporate into the device applications. Right? So this single parameter gives. Now you need not to worry about what is my applied electric field, how much I created. No, simply you measure what is your alpha. Then it is. You know about your K, then you will know about it. You just measure your kite, you will know about it. So from now you will not actually ask what electric field I created, how much I got the polarization and all. But these parameters people are interested. When you look at the data sheet, they will give this is the K value, this is the alpha value, this is my P value. By looking at those values, you have to understand what is actually they are referring to. Got it? So these numbers are important. So when you go on to the higher classes and actually in the manufacturing industry, all these numbers only make sense. Right? Yeah, this much is enough. Now let me introduce next 2 minutes a small thing, then I will close. What is that is? Actually, these are all basics which are on which we will go to the derivation part. So, if any doubt is there in this class, please ask me. Otherwise, from next class, what we do is actually 3 derivations are there in this dielectric materials. Only 3 derivations. Next class, I will do 2 derivations. Monday, no exam now.
No, sir.
Yeah, 2 derivations will try to finish. Easy derivations only. So for that to follow, this background is important. Tomorrow no class, no for us. Right? Monday no exam, no? Exam is there.
Monday.
Then when can we finish syllabus?
Monday in exam is you?
We'll see. Okay, let me introduce this concept for the next class. Types of polarization. So what you are doing, you are creating polarization by applying the electric field. That's all now we are doing. So how many types you can generate it? How many types you can do it? If I ask you to perform certain tasks, everybody has their own style of performing it. So similarly, different materials are there because the world is not same. Many materials are there. Different types of dielectrics are there. They have their own structure within that. They have their own style of responding to the applied electric field. At the end, ultimately, they are generating the polarization. But what is the mechanism inside? You have to look deep into the material. Okay, that is important. So, after generating the polarization, what way it generated? If you summarize all of them, there are 4 types of creating polarization. Type number 1 is electronic type, electronic polarization. Second one is ionic polarization. Third one is, have you heard of these names? Orientational. Then phase charge. 4 types of polarizations are possible. Quickly I will tell and let me close it. The name itself says, actually you need not to struggle or by heart anything. You know the name, you know the mechanism. That's how the names are beautifully created. Electronic polarization. Polarization happens due to
Apply
electric field. You have to apply in every case. There is no exemption. Okay. What is polarization? You have to recall that. What is capital P? Definition. Definition. Dipole moment per unit volume. So you need to have dipole moments to talk about the polarization. So dipole moments, which means it should have a dipole. So what is a dipole? You need to create a dipole, right? What is a dipole? What is electric dipole? Two equal and opposite charges separated with the distance. Very good. So you need to have a separation between the charges. That's all in simple cases. So electronic polarization happens. It's the polarization due to the separation of electron cloud. Simple. Electronic. In an atom, positive, negative center of gravities are at the same time. By applying the electric field, you are separating them. So due to the separation of the electronic cloud from its nucleus, it is polarization happens. That is called electronic polarization. It is happens due to the separation of electron cloud. Simple. From the nucleus. The name. You know what you do if we are asking for the 4 marks. Explain about different types of 4 marks. You have to draw neat diagrams and do it. So how the diagrams look like. So take a material like this and show an atom where you have less than equal charges. Then you say your total charge becomes 0. Therefore, the total polarization becomes 0 when you don't have any applied electric field. But when I apply electric field, what happens? When I apply electric field, which means when E is not equal to 0, your polarization is also not equal to 0. Okay, because after application what happens? This positive charge moves that side, the negative charge moves this side. Negative charge. So there is a separation between them. So inside this small p is there. So this is the electronic polarization. Simple diagram. You need to explain using the diagram how the separation comes. So I already explained, so I am not spending more time on it. Second one is ionic polarization. What is ionic polarization? Ionic polarization is due to the separation of the ion. Orientation due to the orientation of the dipole. Phase charge is due to the accumulation of the charge on the space. I will explain this phenomena in the next class. Okay? We will close it here. Any doubts you may ask. If there are no doubts,